Hello and welcome back to Aerospace and Mechanical Lab 2. Today we are going to talk about the theory behind Lab 3, which is plate buckling and DIC test. In today's analysis, we are essentially going to focus on buckling of plates and strain field measurements, which is compared to a point strain measurements that we have already done. We are going to talk about the different methods of strain measurements. We will learn how to use the DIC device to make the field measurements. Essentially, we will learn the theory behind it, and we will talk a little bit about how to use the strain field analysis. This will of course be followed by a lab recording video in which we'll teach you how to use our DIC machines. Plate buckling in general is a very important phenomena that engineers, mechanical and aerospace engineers, need to be aware of, need to bring in their design and analysis when designing any material. You can see examples of plates that have been buckled due to different types of forces, and these two examples right here are examples of buckling failure. So the material here has not yielded, there is no fracture yet, but we do see buckling, and we have analyzed the Euler column buckling, so we already know that the buckling usually happens before the yield stress of the material, which means that it is an important concept that we need to definitely bring into our analysis. There are a couple of examples of buckling. If you have uniaxial compression loads, compressive loads like this one, your plate buckling is going to look like this. Depending on the mode of buckling, we have already discussed the different modes of buckling. The idea is there will be these type of patterns available if you apply a uniaxial compression. If you apply a shear force, the buckling is going to look similar, but the direction is going to be different. We will see buckling with shear force and uniaxial compression. So far, we have only talked about compression in Lab 1 when it comes to buckling. But you can see here that both shear and uniaxial compression can cause buckling, right? It is not just the plates that see two-dimensional buckling or three-dimensional buckling. We can also have cylinders and spheres that are subject to shear or compression experience buckling. Analyzing these modes of buckling is a bit difficult using the equations and the theories that we have. Like developing a theory to analyze this type of buckling is pretty difficult and pretty comprehensive. That's why we need to think of different methods, right? Other examples of buckling and how to overcome them, for example, to overcome the buckling of plates specifically that are subject to shear or compression force, we can add stiffeners, vertical stiffeners to our designs, whatever they are used for. We can add flanged holes, and we can add a sine wave and isogrid. I'm sure all of you have seen examples of this type of designs that are supposed to prevent or delay the buckling of plates. So the idea is you definitely need to have a good understanding of how your plate will buckle, so you can choose a good preventative mechanism to avoid buckling. Okay, so all of this tells us that the accuracy of the buckling analysis is very important. So we cannot just simplify the whole thing to find a final number, for example, for the critical load of buckling. We need to do a more in-depth analysis. The problems that we might face in this quest of doing a good buckling of plate analysis are the initial imperfections that might be there in our design. So this is not an ideal Euler column anymore. We are dealing with initial imperfections. We might deal with a curved geometry. Again, this is not an Euler column anymore. And we might not be sure of the support conditions. That's also very important in analyzing the buckling. We might also see inelastic behavior of material at different regions. We might see regional yielding happening that might affect the buckling failure itself. So the methods we have is we essentially have two different methods. We can use empirical methods that are derived from testing and experimentation. And the problem with the empirical methods is that they are only applicable to a specific scenario because you have derived the empirical equation for those specific scenarios. And we can also use the numerical tools that we have in our disposal. We are going to use numerical methods later on in the semester for computational fluid dynamics, but for now we want to stick to experimental methods. So the question would be, what type of experimental methods will give us the best understanding of the buckling of plates and the critical load of buckling? That's the question we want to answer. And the answer that we have is the digital image correlation. Digital image correlation is a computer-based process that will help us obtain a two-dimensional, three-dimensional full field surface information. So instead of measuring a strain at a specific point, like what a strain gauge does, we can have the strain field all over our plates, which is going to give us a very good understanding of when and where the exactly plate buckles. And the idea behind this method is pretty simple. We essentially have to create a speckle pattern, and then we are going to track the movement of these speckles as you apply the load. Right? Of course, we are taking advantage of the fact that the stress that we are applying is going to change the thickness and the optical properties of the material, right? This method was developed in the mid-20th century. Essentially, we started development of this in the mid-20th century when we came to the conclusion that the strain gauges were not enough for field measurements, or coming up with field measurements using a strain gauge is going to be a cumbersome task, right? The strain gauges, we already know how they work. As the displacement happens, the resistance of the circuit changes, and that will tell us how much strain we are seeing in our domain. Okay, so if you were to analyze a plate buckling using strain gauges, you have to install strain gauges at every location. And then for the locations in the middle, you have to interpolate your results. Again, not a very accurate representation of the field of a strain that we want to see on our plates. Okay. So in our department, actually, a couple of people got together, published a couple of papers to develop the mathematical method behind the DIC. So in order to actually convert the images we are taking from the speckle pattern, we need to have a mathematical method to convert those to strain fields. And Dr. Sutton, Dr. Cheng, Dr. Ranson, and Dr. Wally Peters were all involved in the process. You can see pictures of them right here. All of these people are retired now. Dr. Sutton comes to the department sometimes. It is not a bad idea for you guys to set an appointment with him, sit down and talk to him. He is one of the icons of our department. That's beyond the point of the digital image correlation. So the digital image correlation was developed mathematically by these guys, and the idea is to take a picture from a specimen, and then as you're applying the load, a couple of pictures, and measure how each of the speckles have moved. So the procedure is you have to create a speckle pattern, of course, usually with a white background and black dots, and then you have to photograph the specimen as you are applying the load. And then these digital images will be gathered, and each of the pixels of digital images after each load application is going to be compared to the previous image. Okay. We are taking pictures of the surface of the specimen, of course, and then we are going to upload all of these frames to our computer to do the analysis. Let me move on. So these are examples of the speckle patterns. As you can see, we usually deal with a white background. Depending on the type of field you want to analyze your speckle patterns, or depending on the type of device you're using, the speckle pattern can be very fine or a bit coarse. The one we have in the lab is a bit coarse because we are using the educational DIC system, which is not as accurate as a research one, but it does a job fine. Okay, so then you upload these speckled images to your computer. The computer, using the mathematical model developed by Dr. Sutton and his colleagues, changes this to intensity graphs, essentially. And then we are going to track the intensity using the computer software, the software that we have. It's called the VIC 2D or 3D, right? As an example, we see that this specific dot here, speckle here, at different times has moved to different locations, and this tracking is going to enable us understand what type of displacement we see here. We can convert this later on to displacement by creating a mathematical function for the intensity and the changes, the rate of change of intensity after each image. And this is a mathematical function. I don't want to go through the explaining of the function, but it's a pretty simple function, but we will never use it. We will use the software. To understand this better, think of this image. Like we have a 9 by 9 pixel images, 81 total pixels, and then we have this sort of pattern, a cross-like pattern, right? This is our first image, and the second image, essentially the intensity is going to be stored like this: zeros for the black dots, 100 for the white dots, and then as you apply the motion or the load, the zeros are going to move. The comparison between these two is going to give us a picture like this. As you can see, this is essentially a picture of how a crack is propagating through the material on a speckle pattern. You can see the crack propagation at different times, and you can see the strain field here, specifically how much displacement we are seeing as a heat map. Of course, these red areas are showing you the highest strain, and this greenish areas are showing you the lowest amount of strain. And the setup we have in the lab is essentially something like this. Well, all of this in one box. We have 2 cameras and a light source in the middle, and you are going to apply a load, make some measurements, and eventually at the end of the lab, what you will need to do is to submit the screenshots or just a recording of the strain field graphs. We don't really need anything extra from you guys. We just want to make sure you have done the experiment. So the worksheet doesn't really have any calculations. You just need to do the experiment and then add the graphs, the strain field graphs, to your worksheet, Word document for the lab memo, and then upload it on Blackboard. Thank you for listening, and please let me know if you have any questions.